When you sing, you create sound that others can hear. But what exactly is sound? And how exactly does your vocal cords create it? And how does it move into someone's ears, for example? And how fast does the sound move? And are there sounds that humans cannot hear? And how can sounds be used to detect obstacles or even create medical images? Okay, a lot of interesting questions. Let's find out the answers. Now, before we begin, let's back up a little bit. You probably know that whenever you disturb matter, like water, for instance, the disturbance propagates outwards. We call that as a wave. But remember, the matter itself does not move. It's just vibrating in place, as you can see over here. It's the disturbance that moves. So waves transfer energy, not matter. And the material, the structure through which the waves travel is called a medium. Now, guess what? Sound is also a wave. That means we can now ask a bunch of questions. First of all, what is the medium through which sound travels? Well, there are several. Sound can travel through air, which is why we can hear things. But it can also travel through water, which is how you can hear sounds underwater as well. And yes, of course, sounds can also travel through solids. So in general, it can travel through gases and liquids and solids. And here's a cool observation. When you talk or sing, you can actually feel your vocal cords vibrating. It's those vibrations that disturb the air, creating a disturbance that propagates outwards. That's sound. And of course, the same thing happens with musical instruments. For example, a guitar string vibrates and disturbs the surrounding air, creating a sound wave. But how exactly does sound propagate through a medium? Well, let's take a slinky to model air particles. Now, there are a couple of ways to disturb this slinky. First, we can disturb it like this. Notice the disturbance moves up and down, but the wave itself travels to the right. So the direction of the disturbance is perpendicular to the direction of the wave. Now, guess what? This is not how sounds travel through a medium, okay? So then how exactly does sound propagate? Well, here's another demonstration. Ooh, this is different. This is also a wave, but you can see it's different. What's different over here is that look how the slinky is vibrating. It's vibrating parallel to the direction of the wave. This is exactly how sounds travel. It's a type of wave where the disturbance is parallel to the direction of the wave. Now, such waves have a very interesting property. Can you see some compressions being formed? It's the compressions that are traveling forward. You can see that, right? That's why these waves are also called compression waves. So sound wave is a compression wave. Now let's switch to a simulation of the air particles. You can see it's very similar to what we saw in the slinky, right? Just like in the slinky, you will see there are regions where particles are squished close together, causing compressions. Same idea, sound is a compression wave. Now here's where it gets really interesting, okay? Now, if you were somewhere over here, as the wave passes through you, air gets compressed and decompressed and then compressed again, right? Because of this, the air pressure changes, and it's this change in the pressure is what you perceive as sound. But of course, sound doesn't just travel in one direction, and that's why in this PhET simulation we can see sound actually traveling, moving in all the direction. The compression waves are traveling in all the direction. But wait, if all sound is just compression wave, what makes one sound different from another? Well, there are several properties. One of them is called amplitude, which actually corresponds to loudness. So what is amplitude, you ask? Well, remember how we talked about compressions causing changes in the air pressure as it passes by you? Well, amplitude is basically a measure of how much that pressure changes. The bigger the pressure change from the normal equilibrium pressure, meaning the pressure when there is no sound wave around, the higher the amplitude. So when a sound wave has a stronger compression, for example, it has a greater amplitude, and so you hear it louder. So in this simulation, actually, we can change the amplitude. Okay, let me increase the amplitude, and you can actually see, oh my God, you can see how close the particles get squished together, right? So the compressions are really high. So when the sound passes by you, very high compression and then decompression. So very big changes in the air pressure. You hear a loud sound. Now let's decrease the amplitude, and you can still see compressions over here, but not as much as before. So the changes in the air pressure isn't as much as it was before. So the sound is much quieter. In fact, try humming softly while touching your throat and then hum loudly. You'll feel the difference in the vibration. That's amplitude in action. Now, if a sound wave has a repeating pattern, we call it a periodic wave. And such waves have something called frequency. It's a measure of how many cycles occur in a given second. Or you can think of it as how many cycles pass through a point in a given second, okay? Now, in this particular example, this is a low frequency. So you can see less number of compressions are passing through a point in a given second, through a given second. So that's low frequency. Now, let's increase the frequency and see what happens, okay? You can see now the frequency has increased. More number of cycles are passing through a point in a given time. So this is a high frequency. How does that affect what you hear? Listen to this low frequency sound. Do you hear it? How it is lower pitch? Now listen to a high frequency sound. You notice a higher pitch, isn't it? In both the cases, the amplitude, the speed, all of the properties were the same. What changed was the frequency. It's the frequency that affects the pitch. Now, of course, our ears can't hear all frequencies. Humans can detect sounds roughly between the frequency of 20 hertz to 20,000 hertz. Anything beyond that range, we just can't hear it, and we call that the ultrasound. Another important property of the sound is its speed. It's literally a measure of how fast the disturbance is propagating. Like you can see over here how fast the compressions are traveling, okay? Now, the speed of the sound depends on the medium through which the disturbance is traveling. For example, in air, the speed of sound is about 340 meters per second. That's around 760 miles per hour. That's fast, but it's way slower compared to light. That's the reason why you see lightning before you hear the thunder. The farther you are, in fact, bigger is the difference between the lightning and the thunder. If you consider sounds in water, they'll travel about 4 times faster than in air. Speed of sound depends on the medium through which it's traveling. Now, like other waves, sound waves can also be reflected at boundaries, as you can see over here, and this causes echoes. In fact, some animals like dolphins and bats actually use sound reflections to navigate and to even hunt. In fact, they're so good at it, they can even determine not just the location, but even the size, shape, and movement of the obstacles. This is called echolocation. I mean, they're literally using the echoes to locate things. We use a similar concept in medical imaging. We use ultrasound waves, we send them to the body, and then these waves, some of it get reflected, some of it gets transmitted and even absorbed, and it all depends upon different tissues that it's going through. Eventually, we collect the reflected waves, they're detected, and they're used to create an image. This helps us see things like the fetus or the beating heart, all without having to use ionizing radiation.